Hello and welcome to the November webinar from the IEA Clean Coal Centre. My name is Deborah Adams and I'm Communications Manager here. We do a webinar every month which is based on our technical reports which are available from our website www.iea-coal.org. Residents of member countries and employees of sponsoring organisations can download our reports at no charge after a one-off registration. Please visit our website for details. Today's webinar is presented by Dr. Qian Zhu on high efficiency power generation, a review of alternative system concepts. Her report on the subject has just gone out in draft and will be published and available on our website early in the new year. If you have any questions during the talk, please use the Ask a Question box at the top of your screen. Add your email address as well so that Chen can send you a fuller answer if we run out of time. Okay, so now I'll pass you over to Chen.
Good afternoon, everyone. My name is Qian Zhu. Today, I'm going to present to you my latest work on high-efficiency power generation, alternative system concepts. Globally, just over 40% of electricity is produced by coal-fired power generating units. Almost all of these units use steam Rankine cycle. Today's state-of-the-art coal-fired power plant can achieve a net plant efficiency of around 45% based on low heating value of coal. However, any further significant increase in energy efficiency will be difficult and have high costs. Also, the maximum efficiency of the Rankine cycle is limited to below the Carnot efficiency. For this reason, efforts are made to develop the so-called unconventional power generation systems, alternative to steam power plant. Let's first look at the fuel cells. Fuel cells are electrochemical devices that convert chemical energy in fuels into electrical energy directly. Because combustion is avoided, emissions of pollutants from fuel cells are minimal, and therefore, fuel cells can produce power with high efficiency and low environmental impact. This figure here shows the basic structure of a fuel cell, how it works, and the 5 main types of fuel cell. The solid oxide fuel cell, SOFC, and the molten carbonate fuel cells, MCFC, are high-temperature fuel cells which offer the best opportunity for thermal integration with coal gasification systems. They also have fuel flexibility. They can operate on hydrogen, carbon monoxide, and hydrocarbon fuels, including coal-derived syngas and natural gas. Fuel cell power generation is an emerging technology. Gas-fueled fuel cell power plants are in commercial operation in many parts of the world. In February this year, the construction of the world's largest fuel cell power plant, the 58.8 megawatts Yunggi power plant in South Korea, was completed with plant efficiency of 47% and extremely low emissions and low water consumption. Coal-fueled SOFC and MCFC systems for large baseload power plants are under development, and there's still some way to go before the first commercial coal-fueled fuel cell power plant can be built. Recently, progress has also been made in the development of direct carbon fuel cells that use solid fuel and can convert the chemical energy in carbon directly into electricity without the need for gasification. Various power configurations integrating a coal gasifier with fuel cell power system are being developed and investigated. The proposed systems usually adopt the fuel cell steam combined cycle or fuel cell gas turbine and steam bottoming combined cycle. Control of CO2 emissions from fuel cell power system is easy because the fuel and the air streams to the fuel cells are separate. Carbon enters the fuel cells, exit as CO2. The residue fuel in the anode of gas can be burned in oxygen, producing a stream of CO2 and water ready for carbon capture. Results from techno-economic analysis of the proposed IGFC systems all indicate that these systems can potentially achieve high energy efficiency up to 60% with almost complete carbon capture and low air emissions. The tables here shows the results from one of such studies. The Magnetohydrodynamic MHD converts thermal energy of a fuel directly into electricity. The MHD generator operates at high temperature, so it can potentially achieve high efficiency. The principle of MHD power generation is shown here. In the open cycle MHD power system, combustion gas or fossil fuel is used as working fluid. In the closed cycle MHD system, seeded noble gas is used as working fluid, which is circulated in a closed loop and is heated by combustion gases using a heat exchanger. Extensive research and development were carried out during the 1970s and the 1990s. Various coal-fired MHD combined cycle power generation schemes, such as direct coal-fired MHD-steam combined cycle, top or tail gasification MHD-steam combined cycle, and a two-loop closed-cycle MHD power plant have been proposed. Among them, the direct coal-fired MHD steam combined cycle, as shown in this slide, is most developed. Many system components were developed and tested, and the conceptual coal-fired MHD power plant designs were completed. Analysis indicated that MHD systems could achieve a plant efficiency of 45 to 55%, have good environmental performances, and would be compatible with carbon capture systems. The development of this technology reached to the point where construction of a complete system was feasible. However, at the time, MHD system could not compete with the advances of gas turbine technology, which made the IGCC look more promising. Therefore, the development focus was shifted to the development of IGCC plants. By the late 1990s, budgets had been cut and the R&D activity stopped. The HIPS that was under development in the US is the indirect coal-fired power system. Here, air is used as working fluid. Compressed air is heated in the coal-fired high-temperature advanced furnace, the heat house, and is then expanded in the gas turbine to produce electricity. Either natural gas or a clean coal-derived fuel gas is used to boost the temperature of the air to the desired turbine inlet temperature. Heat is recovered from both coal-fired furnace flue gas and the gas turbine exhaust to drive a steam cycle to maximize power production. Most components of the HIPS power plant were already available. The only technology needed to be developed is the heat house, including its air heaters, especially the heater located in the furnace radiation section. The development of HIPS took two approaches. One used the fluidized bed coal pyrolyser to convert coal into a fuel gas and the solid char, as shown in this slide. The char is burned in the heat house to heat the air and also generate steam. The fuel gas is burned to further heat the air to the gas turbine inlet temperature. The other approach used a direct-fired slugging furnace. The main advantage of the HIPS is the possibility to have a combined cycle, resulting in efficiencies of 45% or higher, and the plant efficiency of over 60% is possible. The HIPS R&D program had 3 phases. However, after the completion of the phase 2, the R&D efforts were directed towards the high-temperature heat exchangers, and the building a prototype plant as planned for the phase 3 was not carried out. Chemical looping combustion is an indirect form of combustion based on the transfer of the oxygen from air to the fuel by means of a solid oxygen carrier that circulates between 2 interconnected fluidized bed reactors, the fuel and the air reactor. Its main advantage is that it produces a stream of CO2 and water ready for carbon capture. Another advantage is the possible flexibility to co-produce hydrogen or syngas and electricity. Several CLC processes fueled by coal-derived syngas or by coal, as well as chemical looping coal gasification processes, are currently under development. Various CLC-based power plant configurations have been proposed and studied. The results show compared with pulverized coal or oxy-pulverized coal combustion plant with carbon capture, chemical looping-based power plants could achieve higher efficiency, high carbon capture rate, with significantly lower energy penalty and lower costs. Despite COC has attracted extensive research in recent years, and advances have been made. There are still a number of issues that require further investigation. For example, the development of oxygen carriers with high reactivity and stability is still one of the challenges for CLC. There have been R&D activities seeking to replace the working fluid water with one that reduces the parasitic losses, or one that can obtain a better thermal match with the heat source. These works have led to the development of power cycles alternative to steam Rankine cycle. Cleaner cycle uses a working fluid comprised of at least two components with different boiling points, typically water and ammonia. Since the solution boils over a range of temperatures as in distillation, more of the heat can be extracted from the source than with a pure working fluid. ORC uses organic working fluid with low boiling temperature. Goswami cycle is under development, and it uses binary mixture to produce power and refrigeration simultaneously in one loop. All three cycles are developed to operate with low or medium temperature heat sources and can be integrated with the steam cycle as a bottom cycle for improved efficiency. Cleaner cycle and ORC have found applications in areas such as waste heat recovery, geothermal, solar thermal, and biomass power plant. Supercritical carbon dioxide power cycle is an innovative technology using supercritical CO2 as working fluid. CO2 has relatively low critical temperature and pressure, and can be compressed directly to their supercritical pressures and heated to their supercritical state before expansion, so as to obtain a better thermal match with the heat source. Supercritical CO2 cycle could potentially achieve higher thermal efficiency and has the potential to replace the Rankine cycle in both topping and bottoming cycle applications. Another advantage of a supercritical CO2 cycle is the extremely compact turbo machinery designs, as shown on the left in this slide. As due to its high density of supercritical CO2, the closed-loop Brayton cycle using supercritical CO2 for power generation from coal is being investigated, but it is still in the early stage of development. The picture shown in this slide is the parabolic mirror type concentrating solar thermal facility that was built adjacent to the existing Camille coal power generating plant in Colorado, USA, for the Colorado Integrated Solar Project. In a solar coal hybrid system, solar thermal energy is usually used to supplement the steam cycle to reduce the consumption of coal in the production of electric power at the plant. the steam produced by solar thermal energy can be used to heat the boiler feed water, or after being further heated to power the steam turbine to generate electricity. The steam thermal energy can be also used to preheat the combustion air. A few solar boost coal power projects have been carried out or are under construction at the moment. In conclusion, coal will continue to play an important role in the global power generation. The technologies for power generation systems alternative to steam Rankine cycle are under development, and some have achieved significant progress in recent years. If these technologies can be developed into practical systems, they could ultimately have a significant impact on coal-based power generation. And I'll stop here. Thank you for listening. Any questions?
Qian, thank you very much for a really interesting and informative overview on these new concepts that are being developed. While we wait to see if any questions have come in, I'd like to remind listeners that the PowerPoint of the webinar will be available to download from the webinar page of our website later on today. Okay, we've got a couple of questions come in. This is the first one, Qian. The fuel cell power plant in South Korea that you mentioned, could you give us a bit more information on the plant, please, such as its current status and emission levels?
The plant is a gas-fueled, the heat and power combined power plant. The plant, I think, is in operation now. Its designed emission value is NOx is 4.54 gram per million megawatts hour. For CO2, it's 0.045 gram per million watts hour. And for particulates, PM10, it's 0.009 gram per million watts hour, which are very low.
Okay, thank you, Qian. There's another question here. How does the supercritical CO2 cycle efficiency compare to steam cycle efficiency?
The earlier academic research work showed that for the cooling water temperature of 5 degrees C and a turbine inlet temperature of 700 degrees C, the reheat supercritical CO2 cycle efficiency is higher than steam cycle, double reheat steam cycle efficiency, and it could be higher than 50%.
Wow, okay. Here's another question. Do you know, Qian, which is the largest chemical looping pilot plant that's operating?
I know Alstom is having the COC pilot plant, which is doing the tests. I'm not sure which one is the largest.
Do you know the size of the Alstom plant or not?
Oh. Sorry, I can't remember the size, but if you read my report, the information is in my report.
Yeah, that's a very good point, Qian. There's a lot more detail in the report. The draft is available, I think, or
No.
the draft will soon be available, and the final report will be available, as I said, to residents of member countries early in the new year. Okay, well, there don't seem to be any more questions come in, so I'll just remind you that the next webinar is on Wednesday, 17th of December at midday, midday UK time, when Dr. Leslie Sloss will give her presentation on the outlook for environmental equipment under new mercury regulations. If you do have any more questions or comments, please email them directly to Qian. Okay, thank you very much for listening. Goodbye.